There you go. We're off again. We're back. We're back learning TensorFlow. Working on the Udacity course. Where did I put that? It's been a while. I've been out holiday. Was it here? No, it was TensorFlow itself. Examples, Udacity, and then in here I think this is where I found the open up notebook. So for today we're working on assignment 3. I think I got that wrong in the title. Working on the third assignment. That's better. That's this one. I think. Or am I working on this one? Nah. This one was done. We're on number 3. Let's just get a refresh of what that was about. Use regularization techniques to improve a deep learning model. Okay. Some steps have been implemented for you. That's good news. Let's just watch the intro one more time.
Why did we not figure out earlier that deep models were effective? Many reasons, but mostly because deep models only really shine if you have enough data to train them. It's only in recent years that large enough data sets have made their way to the academic world. We'll look at another reason now. We know better today how to train very, very big models using better regularization techniques. There is a general issue when you're doing numerical optimization, which I call the skinny jeans problem. Skinny jeans look great. They fit perfectly, but they're really, really hard to get into. So most people end up wearing jeans that are just a bit too big. It's exactly the same with deep networks. A network that's just the right size for your data is very, very hard to optimize. So in practice, we always train networks that are way too big for our data, and then we try our best to prevent them from overfitting. The first way we prevent overfitting is by looking at the performance on our validation set and stopping to train as soon as we stop improving. It's called early termination, and it's still the best way to prevent your network from over-optimizing on the training set. Another way is to apply regularization. Regularizing means applying artificial constraints on your network that implicitly reduce the number of free parameters, while not making it more difficult to optimize. In the skinny jeans analogy, think stretch pants. They fit just as well, but because they're flexible, they don't make things harder to fit in. The stretch pants of deep learning are called L2 regularization. The idea is to add another term to the loss, which penalizes large weights. It's typically achieved by adding the L2 norm of your weights to the loss multiplied by a small constant. And yes, yet another hyperparameter to tune. Sorry about that. The nice thing about L2 regularization is that it's very, very simple. Because you just add it to your loss, the structure of your network doesn't have to change. You can even compute its derivative by hand. Remember that the L2 norm stands for the sum of the squares of the individual elements in a vector.
This is the loss.
Each of these formulas gives you the derivative of the L2 norm of a vector.
So So this is the loss that we know about, and then it adds this thing. This B sign times that thing. We know about the loss, so that's good. So I think if I just look up L2 regularization. I hope it makes sense. It needs to make sense before I go any further. I think I've seen this before. Is tuning or selecting the preferred level of model complexity so your models are better at predicting. If you don't do this, your models may be too complex and overfit or too simple and underfit, either way giving poor predictions. If you least square fit a complex model to a small set of training data, you will probably overfit. This is the most common situation. A way of testing how good your models are at prediction, for example, using cross-validation or a set of validation data. A tuning parameter which lets you change the complexity or smoothness of a model. Basically, you adjust the complexity parameter or change the model and find the value which gives the best model predictions. Note that the optimized regularization error will not be an accurate estimate of the overall prediction error. So after regularization, you will finally have to use an additional validation dataset or perform some additional statistics and analysis to get an unbiased prediction error. Will not be an accurate estimation of the overall prediction error. Okay. An alternative is using cross-validation testing to use... An alternative to using cross-validation testing is to use Bayesian priors or other methods to penalize complexity or non-smoothness, but these require more statistical... Okay. Right, so I need to understand what the L2 is specifically. Y is better than L2. What is the difference between L1 and L2? There are already a couple of pretty good answers that explain L1 and L2. I'm trying to complement them from a purely practical point of view. Thank you. That's what I need. Would someone disagree with Andrew? Don't disagree with Andrew, man. It is well known, as explained by others, that L1 helps perform feature selection in sparse feature spaces. And that is a good practical reason to use L1 in some situations. However, beyond that particular reason, I have never seen L1 perform better than L2 in practice. To be clear, I don't think I am the only one to be in this situation. If you look at on this issue, you will see how they have not seen a practical example where L1, okay, as opposed to what explains in this feature selection. L1 versus L2 and rotation. I would say that as a rule of thumb. Okay. Oh well, he's not really actually explaining what it is. Ha. Let's have a look at it. Look at it again. So adding to the loss You add. I'm not sure what this thing means. These vertical lines. Math notation to typing characters. Vertical bar. Sorry. Oh, never mind. Well, this translates to this, where you're taking the sum of all the weights squared divided by 2. Okay, what was actually the question here?
It's in a vector. Which of these formulas gives you the derivative of the L2 norm of a vector?
The L2 norm of a vector. Christ. I don't think it's this one. Because where does he get the 3s from? It could very well be this one, but I want to say W because I don't even know if you answer.
You know that the derivative of 1/2 of x squared in one dimension is simply x. So when you take that derivative for each of the components of your vector, you get the same component. So therefore, the answer is the third one.
And this makes sense because x well, kind of makes sense to me. Okay, so that was that. Let's just start off with the exercise because I need to change the, okay, that's good. Let's load the pickled file. Reformat into a shape that's more adapted to the model we're going to train. Data as a flat matrix. Labels as float, one hot encoding. So instead of it being 200,000 2828, it's 200,000 784. Okay. All right. Accuracy is this. Predictions, labels. Problem 1. Introduce and tune L2 regularization for both logistic and neural network models. Remember that L2 amounts to adding a penalty on the norm of the weights in TensorFlow. You can compute the L2 loss for a tensor using an n.L2 loss of tensor. The right amount of regularization should improve your validation and test accuracy. Whoa. Okay, I guess I can just copy paste what we had in the previous exercise. Right. Which was steps. Let's run it. Excuse me. That's this side. I think it's all of this. And this is the run. Shut down. So let's go through this again. Batch size. This was that the batch size of the stochastic gradient descent. So that would be here. Yeah, where is batch size used? It should be when you're running it. Yeah, batch size. Number of features is 784. Num nodes. What's that used for? Yeah, that's what we were going to. That's the number of nodes in the hidden layer. In this example. Okay. Here you're creating a placeholder. The constants. Weights input is a weight variable. There you go. Bias variable. Those are just zeros. Yeah, these namings weren't very good. So you multiply the train data set by the weight input plus the biases input. And then you ReLU that. Now you do it again. These namings are very bad though. But yeah, doesn't matter. Loss equals the reduce mean of this thing here. Softmax cross entropy with logits labels. Prediction for the training. So let's just run this. And then let's do 5,500. %. Okay. And then they're saying amounts to adding a penalty on the norm of the weights to the loss. Norm of the weights. Adding a penalty on the norm of the weights to the loss. And the loss is here. We need to add reduce mean. In TensorFlow you can compute the L2 loss for a tensor T using L2 loss. So can I just say loss regu equals nn dot, what was it? L2 loss of loss. No L2 loss. Oh, that's because it's called loss. Okay, a loss. And then you optimize that. Doesn't make TF dot. %. Awesome. TFNN L2 loss computes half the L2 norm of a tensor without the squirt. Without the square root.
Playing my hits.
This is my first time. I'm sorry.
You can compute the L2 loss for tensor T using so if I just do 5 times this. So do I need to square root this again? No, I don't.
I thought you said I was beautiful.
You are beautiful. Everything's okay.
Yeah, I guess you need to make this a not a constant, but a value as well. Remember that L2 amounts to adding a penalty on the norm of the weights. The loss. This all seems to be 10%. Is it like I think I should give it a. I guess that should also be a placeholder. Of like float. Oh no. 32. Shape of which is 1. Is it? Is it 1? No, it's not right. It's not definitely not 1. It's I don't know. That's not gonna work, is it? It's not. F train. No, that's not it either. I'm just doing stuff here. I'm not actually. No, I don't know what I'm doing anymore. It's not the way to go. Let's see how this guy fixed it. What? Wait a second. Wait a minute. That's what I did, right? What is this beta regio? Oh, that's the one that I was where I was. Oh, I wasn't too far off, to be honest. Let me juggle some things around, and I should be good to go. You don't need to give it a shape, and yeah. So you have loss. I wasn't too far off, that's good news. Happy with that. But instead of doing... Yeah, so it was loss. So it's loss plus this times that. I think that's, oh no, this is just like this. Placeholder 2. Oh, and then here he does something with the... Here he just gives it a number. Okay. Sure. It's called TF Regu, I think. Like that. So what did I do wrong then? Well, I didn't initialize the placeholder down here. That's probably what I did wrong. And you also need to... Oh, I think I actually did that, so... Let me just move this up here, it's cleaner. There you go. Oh. Yeah. Oh, I can't do that because I need to. How did he do it? Oh. Ooh, I did it actually. Did it completely wrong actually. That's funny. Completely wrong. Right. So you need to pass it to weights and not the... Okay. Cool. Mm-hmm.
You don't make up for your sins.
So how much is that actually?
You do it in the streets. You do it at home. The rest is bullshit and you know it.
Is that 0.001? Just wait for this to finish. One more to go. %. 001. Okay. Awesome. Cool. Problem 2. Let's demonstrate an extreme case of overfitting. Restrict your training data to just a few batches. What happens?
Hits.
Add a delta. Nerdy talk in this comment section. This is from 2011. Wow. Wow. Localhost. Nice, man. Nice, bro. Okay. Let's demonstrate the extreme case of overfitting. Restrict your training data to just a few batches. What happens? Do I copy all of this in one again and again and again and again, or can I just use? Can I just copy this part? I can probably just copy this part. Step times batch size. Copy this as well. And we will say that optimizer protections for training this data.
Allow me to introduce myself. Who knows what dastardly
Oh, it's here, isn't it? So feed ticked. Batch data. Train data offset. All records. Oh, let's get that proof from up here somewhere. Oh, okay. I'll just change it here. It's fine. It's whatever. So I will say reformat. Train data set. Zero 5,000. I think this is what they mean that I'm supposed to do. Okay. Oh. Train data Did I get that wrong? We did a set. No. And then we'll rerun this part again. And then this part again. Nope. Wait, did I miss a part? Uh-huh. That's no problem. Oh, I think this means... Yeah. This is what I need to... This was the exercise, right? Up here again. Restrict your training data to just a few batches. What happens? I think it's this thing here that breaks it because it can't reshape. Maybe we need to do a bit more than 5,000. Let's do 50,000. Oh, 30,000. What's supposed to happen? Oh. Is it just a... batches? Num batches, where does it use this? Num batches, offset to step. Batch size. Yeah. So they're just talking about lowering this down. With all of the data. Step divided by num batches. Step. What is step? Steps. Batch. For step and range num steps. Batch size. Since there are far too much parameters and no regularization, the accuracy of the batches is then 100%. Generalization capabilities is poor as shown in the validation and test accuracy. Okay. I need to understand what's going on. Why is this 100% and this is very low? For step in num of steps, so there's 10,000, there's 1,000 steps, so it would be 1 divided by the batch size. So it creates a mini batch. Trains it. Okay. Okay. I think we're 1 hour in. I think I'll cut it here. Continue with this tomorrow. Thank you for watching, guys.